Okay, so we have been wandering into renewable resources like the forest and talking about forests and trees, but generally some of these arguments could also apply to other renewable resources. So hopefully you can see the forest from the trees, so to speak. But you know, sort of viewing these forests as our kind of running example here. So and something that I wanted to point out is so we've been talking. So if you think about it, like a forest is viewed as a little thicker here maybe, is a collection of stands. So if you're not familiar with this term stand, then a stand is basically an area of forest that is uniform in composition, age, etc. So if you happen to own a large region of forest as such, then we can divide that large region of forest up into stands. So just do that this way. I probably could have thought this through better to make these more equal, but we can view this as stands. This is a ugly color here for this. Where within every stand, then you might have trees of the same age, but across stands, they might be of different ages. And so we've been talking about this optimal aging problem, which determines when to cut and regrow. Now, you can have across these stands, you might have a single time that you cut, but a single duration that you cut. But if this forest grows in an area of the world where you get basically the same type of growth all year round, then you could stagger when you're doing those cut times. And so you might make it so that you cut this year, and then this one is maybe next year. This one is this year plus 2, maybe this is year plus 3, and then maybe over here you cut this year, and then you repeat that pattern. Year plus 1, year plus 2, year plus 3, and then again this year. And so you can actually have the same rotation lengths but offset cut times. And all of the analysis that we're doing for a single stand will apply. But what is interesting about this, if you're trying to translate an optimal aging problem into, let's say, a conservation problem, then if you notice that this year we're only cutting 3 out of the 9 stands in this forest. And so most of the forest is growing along its way. And so effectively, so when you think of this forest management, you don't have to think of forests that grow and grow and grow and then are totally cleared, and then grow and grow and grow and then totally cleared. what you can actually think about in this forest management are different portions of the forest are cut at different times, so that at any particular time there is forest that is older than other forest there. So if, for example, you decide that your rotation length is going to be long enough that you're going to support old growth forest, then even though you eventually cut, there will always be some old growth forest in your forest, because you're only going to cut a fraction of it at a time, because the rest of it won't be ready to be cut yet. And so if you need to maintain habitat that is only lives, if old growth forest is an important habitat for certain species that you're trying to maintain, then this rotation idea may still allow them to have a home, because they can move from one stand to the next. If this stand is cut, this stand may be of adequate age that they can still live there. So, so there's a possibility to maintain some presence of old growth forest across this whole forest, even though you're cutting individual stands at a time. And so if you can encourage longer rotation lengths, what you will end up encouraging is a longer average lifetime of the trees in this forest as a whole. And so that's why choosing those rotation lengths is effectively also setting habitat parameters. And so that's something that we're going to start to get into now. So last time we talked about just what you want to do if you were to maximize wood volume, which we're going to find out is not something anyone would want to do. And now we're going to start to add economics into that. And then if we have time, this time, we will then add habitat value into that. And if we don't, that'll be the first thing we start with next time. So that's where we're going here. Okay. So remember from last time, we talked about if we focus on an individual stand, so focus on an individual stand, and then we are again focusing on the so-called optimal aging problem. And the idea here is that I would have models of how trees that I'm focusing on in that stand grow over time, and how much wood volume that they produce over time. And one of those models might look like this one. So I'll just draw an axis here over time. And this here is, so this is time t, and this is volume. So this is volume of wood produced. So we're focusing just on timber benefits. So you're cutting the trees down and getting benefits from the wood. And so this volume might look like a function like this one, and this functional form is not meant to make anyone feel anxious or anything, just saying that you could imagine that there is some statistical model that someone's fit and decided that this was the best shape. And if we plot that thing out, it looks something along the lines of this. So if I concentrate, maybe I can get something that looks halfway decent, where we have some point here, T max, I'll call it. And at T max, you have the maximum volume in an individual stand. So if you wait this long, then you get this maximum volume. And now if I think about this, what does Tmax correspond to? Well, that corresponds, if you have kind of a calculus mindset, then that corresponds to where dV dt which I also will call V prime, is equal to 0. If you're not comfortable thinking of it that way, then we can say it's where delta V is equal to 0, where delta V we're going to use as the change in volume from one year to the next. And so up here, the delta V is equal to 0. And so basically we're saying that if you want the maximum wood production from a particular tree stand, just in one cycle, so we're not worried about all the cycles, just in one cycle, then you keep measuring the trees, and you have some estimate, maybe you have some overhead, a drone that goes over and measures canopy or whatever, it has some estimate, and there's going to be some year where you're going to look at the growth and you're going to say, there really wasn't any growth this year. That it was the same volume from last year to this year. After that point, you can be pretty confident that you're going to actually see declines. So in other words, some of your trees are going to start dying. And so that is the best time to harvest if you really want the maximum volume in a particular stand in a particular rotation. Now, the question is, though, if we want to harvest over a long period of time, to say, what is the maximum wood volume we can get over long periods of time, then is it worth waiting on this slow stuff here? I mean, notice here that we have fast growth in this region, and then we have slow growth and eventually halting growth entirely in this region. In the ideal world, we would take this fast growth and just let it keep on going. Our trees would just keep going more and more, and we would take longer and longer to harvest. But we don't have that, and we have this slow growth. And so really what we would, there's going to be some point where we actually want to harvest early, and that harvesting early is going to get rid of the slow growth and replace it with new growth, which will have fast growth again. So rather than say you hit a particular point here, you could continue to let the trees grow, but they're going to grow at a slow rate. And so what we're saying here is that, well, what if you cut them down here and then replant them over here? Well, then they initially grow at a kind of a slow rate, but then they get a large region of fast growth rate. And that's kind of what I want. I want to maximize the amount of time I spend with fast growth. And I liken this to a bank. Imagine if all banks were organized out there so that you had low interest rates initially, and then high interest, and then low again. And then in fact, even negative interest rates where you start losing principal. Well, if you're in such a bank, what would you do with your money? Well, initially you got to put your money in somewhere. So you put it in a bank and you live through these low interest rates. And then that bank starts giving you that loyalty benefit, and they raise their interest rates and your money starts growing faster. But eventually they back off the loyalty benefits and the interest rates go back to the slow interest rates that they gave you at first. Now, at this point, if they're giving you low interest rates, low growth, you may as well move your money into another bank that starts you off at low interest rates, because at least after the move, you know that eventually you'll be in fast interest rates again. And so that's really what we're doing with this rotation, is that we live through an area of low interest rates so that we get fast growth. And then at the point where the fast growth backs off, rather than going to these slow rates, we then cut to get back into these slow rates so that we spend as much time as possible in the fast growth time. That's what we're trying to figure out. So then the question is, where do we do the cutting then? Exactly where do we do that cutting? And so what we talked about last time is that, well, if we're talking about maximizing the volume over a long period of time, then so maximum volume over long period of time, then what we've really got is, if we zoom out on the stand dynamics, then we've got time here, and we're going to come up with some rotation length. I'll call it TR. And we know the number of rotations is just going to be equal to the total time we're considering divided by TR. And then the actual growth per rotation is going to be that growth curve repeated over and over again. Where this here is V of t, and at every point, we've got V of TR. And so V of TR is how much we get per rotation. So this gives us V of TR, and this gives us V of TR, and so on. So every rotation gives us V of TR. It's dumping out this V of TR. So how much wood do we get over time? Well, over time, then we are going to get time divided by TR multiplied by the yield per rotation, V of TR. And so this is the per rotation yield. And I can rewrite that as the length of time times V of TR divided by TR. Now, if the total duration that I'm going to engage in this venture is fixed, so if this length of time is fixed, then the only way I can maximize the total amount of wood that I produce during that long duration is to maximize this ratio. And this ratio is a ratio that we called the mean annual increment. Or MAI. And if you maximize the MAI, so if you choose a TR that maximizes the MAI, you will maximize the amount of wood produced. And so maximizing MAI has the effect of maximizing production of resource. And so because of that, this is referred to the MAI maximizing choice, the biological rotation. And so you can, if in the I think in the course notes that I've posted online, I think I have a calculus derivation of how to solve for the maximal, for the MAI maximizing approach. And actually sorry, my tablet was sitting on my space bar, and so my course notes were paged all the way to the bottom and I was stuck. All right, so yeah, if you're interested in the notes, I've done kind of a calculus approach to show you exactly how to solve for TBR mathematically. I'm not going to do that here. I'm just going to sort of show you graphically as I did last time. And so the idea is that we go back to this graph here that we have, then if the MAI at any particular rotation length is just the slope of the line that connects the origin to that rotation length. So the slope of this line gives you the MAI for T max, because that's just the rise divided by the run. So in order to maximize my MAI, I need to find a line that's tangent to this curve that has the maximum slope. And that line is going to be, I'm just going to draw a straight line here, try to pierce. So right there, this point right here. That point right there is the TBR, the biological rotation, and it has the maximum slope, which by the way is equal to V TBR divided by TBR, that intersects V of t. And so that is a graphical way to solve for TBR. So if I give you any drawing of a volume plot over time, then you can draw a line and rotate it up until it just, graces, that it just glances against here, this volume. And then that point right there will be your biological rotation. And it will be shorter than where you'd get if you wanted to produce the maximum amount of wood per rotation. So at this point, this is dealing with the trade-off where we're trying to increase the number of rotations and increase the yield of each rotation. So that's what this MAI maximizing does. So this is the MAI maximizing. All right. So can we get a better idea of what's going on there? Well, if what we're doing is so if you think about the tangent curve here to this slope, this MAI maximizing condition is effectively the condition that the derivative, or the delta V, the derivative of the volume, which is approximately equal to the change in volume from year to year, that thing is equal to the MAI. And so that's at the point, this is the condition for, and I guess I should write TBR there to make that even clearer. So this equals V TBR over TBR. So this here, maybe I'll just put delta V next to it. This here is a statement of the biological rotation. So this is saying that in the biological rotation, you measure your delta V every year. You say, how much did we grow in the last year? How much did we grow in the last year? And so on and so forth. And eventually, the amount that your instantaneous growth rate, delta V, will fall to your long-term growth rate. So you can think of delta V as an instantaneous growth rate. And you can think of the MAI, V of t over t, as an average growth. It's a long-term average. And so what the biological rotation is doing is it is cutting at the instant where your instantaneous growth falls to your long-term growth rate. So your instantaneous growth rate falls to the long-term growth rate. So that makes sense, because you're saying that if the instantaneous rate is lower than the long-term rate, then what that's going to do is going to pull down my long-term rate over time. If I want my long-term rate to be maximized, then I always want my instantaneous rates to be at least the current long-term rate. And at the instant the instantaneous rate drops to the long-term rate, then I need to cut and regrow so I can get back on the fast growing curve again. That's what the biological rotation is doing. So I just wanted to highlight here, because this is going to become important as we move on to the other rotations. The longest rotation is when delta V is equal to 0. So, so we actually then wait for delta V to get all the way down to 0. In the biological rotation, we have a new threshold. We wait for delta V to reach V divided by T. So this here is going to be strictly greater than 0. And so now our delta V is falling, and it's going to stop at a different point. So what I could do is I could actually plot those things. And so I could plot over here. Let's see if I can get this right. So I would plot here, this is going to be volume per year. And what the claim is that there is some MAI function which looks like this. So that there is my MAI, which is V of T divided by T. And then there is a delta V function, which is my instantaneous. You can think of it as, for those of you that are more comfortable with the kind of calculus interpretation, you can think of this as the derivative of the volume functions, V prime. But if I were to draw that, it starts slow, but then it gets fast, but then it comes back down. And so it will be something that looks more like, say, this. Yeah, that'll do right there is good. And so this here is my, this is like dV dt, or V prime, which is just like delta V, which is my change in volume from 1 year to the next. And so down here, this is where, this is T max, basically, where delta V is equal to 0. And up here, is TBR. And that is where delta V is equal to MAI, which is just V T over T. And so the biological rotation, and this happens to occur at the maximum MAI, where delta V is equal to MAI. And if you think that through, it kind of makes sense why that is the case. So I'm drawing this graph because as we move from rotation to rotation to rotation, there's going to be a common theme here, where effectively what we're doing is we're moving the threshold for on this on this delta V curve. So here we're saying that if we focus just on a single rotation, then we wait for the delta V to fall all the way to 0. If we instead want to maximize the amount of wood produced over long periods of time, then we wait instead for the delta V to fall to this threshold, which is where, which is the MAI. It falls to VT over T. And so as we add in more economic factors, then what we're going to see is we're going to shift this delta V threshold up even higher, which will cause the rotations to get even shorter. So before we go on to a new rotation then, are there questions about this with the with our biological rotation. Does that make sense so far, the biological rotation? Okay. And if you have any questions that you're shy about and you'd like to put up there, then again, don't forget, you can always do post those questions anonymously at that link there. All right, great. Okay, so now let's add some more economic factors into it. So the big question here is, what about the time value of money? And this is something that I think came up in some of the muddiest points. Is that why haven't we involved the time value of money in this biological rotation? Because it's just biological, it's not a totally economic rotation. So in the time value of money, what we really now need to say is it worth waiting the 71 years or whatever it ends up being to get this extra wood out? Because if you think about it, not only, I mean, if I go back to thinking about this plot here, then it's true that this is like an interest rate. If growth from a tree is like an interest rate, then I really need to be comparing it to the interest rate that I'm getting from a bank. Because if the interest rate I can get from a bank is actually better than the interest rate that I can get from a tree, I better cut down that tree, turn it into dollars, and then put those dollars in the bank, because it'll grow faster in the bank than it will as a tree. And so that's what we're modeling, is that type of decision making. So we need to now compare this growth rate with the growth rate that you would get at a bank. And so how do we do that? And so what I'm going to introduce here, because now I need to be able to convert wood into dollars. So I have to introduce a couple of variables. And so I'm going to say I got P, which is the price of timber per unit. And then there was a question last time about, well, what about the cost of cutting this stuff down? Well, then we'll introduce C, which is the cost of that timber. And so you can see that net, I'm going to get P minus C returns per unit. And then I've got my volume function, and I am mainly concerned with whether I cut this year or wait till next year to cut. So I'm just going to focus on VT0, which will be the volume, the stand volume this year. I guess I'll write stand volume. Volume, not UOUM. And then I've got V of T1, which is the stand volume next year. And I am going to then define delta V, as we've already talked about, as VT1 minus VT0, which is the year-to-year change. Okay. And then because banks are involved, I have to involve an interest rate. So I've got a discount rate or interest rate that I need to compare to. All right, so this is one of those things where I need to kind of think back to Hotelling's rule and no arbitrage conditions and set up something similar for this renewable resource. And so the rule, the kind of Hotelling's rule-like rule that, that I am focusing on here is to cut when the present value of gains from this year from selling my trees are going to be greater than the present value of gains that I would get from doing the cut next year. So I cut when P minus C times V of T0. So that is the benefit I get. And there's a question here. Is Hotelling's rule just a fancier version of what we did in unit C? Well, so this is, I'm saying it's like Hotelling's rule. Oh, I'm sorry. I'm remembering my units. Yes, Hotelling's rule is a fancier version of just net present value. It's applying net present value to a non-renewable resource. So he gets the name for it because he studied non-renewable resources. And okay, so, and this rule will be named after another old dead white guy because that old dead white guy was interested in renewable resources, but it's exactly the same math. So smart people could have come on, like a lot of people could have come up with these things because they're not that complicated, but the first ones to do it tend to get named for it. But in the end, it's all net present value. So there is a, so this right here, this is our present value of harvesting this year. And we are going to cut when that is greater than P minus C times V of T1 divided by our discount. So this is our time, our marginal rate of substitution. So this gives us the present value of harvesting next year. And so that is how we set up the math. And now we just need to solve for this, for the T naught or the T0 that makes this happen. Because if we can solve for that T naught, that tells us the length of time up until when we reach this cut condition. And so at that length of time, when we reach this cut condition, that will be our rotation length for this rotation, which by the way is going to be called the Wicksell rotation. So I'll write that here in a second. So with a little bit of algebra, so so if you look at this thing, I'm deciding, yeah, so if we look at this thing here, it turns out that for this Wicksell rotation, this P minus C cancels out of both sides. So that's super convenient, right? That you can just divide both sides by P minus C, and then you're just left with the volume from this year is greater than or equal to the volume from next year divided by basically a discount. So, so we're discounting by the interest rate there. So this here is equivalent to just saying the volume this year is greater than or equal to the discounted value of the volume next year. That is an alternative way to formulate this. So, but I'd like to put this into the kind of delta V formulation. So you do a little bit of algebraic rearrangement, and what you find out here is that you end up getting that this rule is equivalent to saying that you cut when the interest rate from the bank is greater than delta V divided by the current stand volume. And so this is the bank interest rate. And then you can view this as kind of the natural interest rate. So it makes a lot of sense. So if we view the tree as a bank, we leave our money, in other words, we leave the trees growing in the tree bank up until the point at which this quantity here, delta V over V, when this quantity, which is like a fractional change, when that fractional change falls to the interest rate I could get at the bank, cut all the trees down, sell them, turn them into dollars, and then put those dollars in the bank. And then they will grow faster in the bank. Meanwhile, you can replant, and then your new trees will be at their high interest rate again, and they'll be able to generate more revenue for you than the bank could. So it's this constant thing of using the trees to generate higher interest rate to the bank until they fall to the bank's interest rate, then put them in the bank, and then restart the thing all over again. That is the so-called Wicksell rotation. Which I'll call TWR. So we have the biological rotation, TBR, and now the Wicksell rotation. And so in this case, yeah, the T0 in that expression is that Wicksell rotation. All right, now, what I'm just going to slightly rewrite that, just a tiny bit. And if I take that Wicksell, so I'm going to go to the next page, but I'm going to focus on this thing down here. I'm just going to rewrite that just so it has a delta V on the left-hand side, okay? And so the Wicksell rotation, another way to write the Wicksell rotation is to say it's when delta V is greater than or equal to R times V TWR. And so I just took the R, I just took the V, the denominator here, and I multiplied it so that I brought it up here. So it's all in this. And I meant to actually say, I said greater than, but I meant to say less than. So I'm going to erase that. And so this is the condition to cut. Cut when this occurs. And so you can think this is year to year growth falls to interest rate R times the current volume. So this is bank interest. And this is the current volume. So that is our delta V interpretation of the Wicksell rotation, is that we take the current volume as the capital asset, and it's delta V is how much additional interest you're getting from leaving it as a forest, and R times V is going to be the additional interest you get by converting it all into dollars and putting it into the bank. That's the Wicksell rotation. And the reason I like to write it this way is that it allows me to go back to that plot that we started with. So I'll just redraw that plot, and you can feel free to not redraw it. You can just keep adding to it if you'd like. But usually people tell me they like me to redraw things because it slows me down. And so this here is going to be our volume again, and I'm just going to try to redraw a curve similar to the one I already drew. And so we knew that on that curve, we have when T max occurs when delta V is equal to 0. And then we also have that the biological rotation occurs sometime before that. Where the delta V falls to the MAI. So the biological rotation is where delta V falls to basically VT times 1 over T. So it falls to the MAI. And I wrote it that way for a reason that, well, as a product, for a reason which I hope will become clear in a second. And so what the Wicksell rotation does is the Wicksell rotation basically is where the delta V falls to, so I've climbed up in delta V. And so so there's going to be another point, let's say it's here, for example. And I just picked that point arbitrarily. And this will be where delta V is equal to R times V over T. And so if I set R equal to 0, I can make T Wicksell rotation go all the way to T max, right? Because at that point I can say, just let the things grow until they stop, returning any interest. Alternatively, if I let my interest rate go up high, so if I increase my interest rate, then I can cause TWR to effectively go to 0. So this is for, R goes to infinity. So this is for very large R. And so what we end up having here is, usually this delta V threshold will be, usually trees will grow, take so long to grow, and the interest rates will be such that this is the normal ordering of things. The T max will be here, the TBR will be here, and the Wicksell rotation will be somewhere there, so that the rotations are getting longer. So the delta V threshold is getting higher and the rotations are getting longer. But in theory, you could set interest rates that move the Wicksell rotation up and down this curve, that move this way and this way. But in general, we see the pattern that the delta V threshold gets higher and rotation gets shorter. And so the general thing here is as I go this way, then delta V growing and TWR is generally less than TBR, which is always less than T max. And that's generally, in most cases. All right, that's my summary of the Wicksell rotation before we move on to adding another complication. So before we add something else to this rotation, are there questions about the Wicksell rotation, about just adding in the time value of money? So I guess I could summarize that the Wicksell rotation includes the time value of money. Any questions about that? Is that pretty clear?
Yeah, that's pretty clear.
Great, thank you for the confirmation. That's actually very helpful. All right, so let's move on then. All right, so that was our Wicksell rotation. And so this so far has assumed that the only thing that I can do with the land is grow trees on it. So if I'm stuck growing trees on it and I want to maximize my revenue over a long period of time, Wicksell rotation is where it's at. But of course, there are other things that I can do with that land. So right now, again, I'm modeling decision-making of a rational landowner. I haven't gotten to what's efficient for society yet. That'll be like the last thing that we talk about. But at least when I'm just thinking about what, if I'm modeling economically where I think a landowner is going to naturally end up, just with market-based forces, then that's what I'm trying to then add everything in here. So the other thing the landowner is going to consider is that the other issue for decision-making is the value of the land itself. And I don't mean the trees, the actual land under the trees. So there is an opportunity cost. So growing timber generates an opportunity cost of what you would otherwise do with the land. So you could sell the land and have someone put a parking lot there instead. You could instead of growing timber, you could grow sunflowers. You could, there's all of these different things that you could do with the land. And so we need to sort of figure out, how does the rotation length change given that so in a world where you've decided that timber is still what you want to do with the land, the fact that you have to deal with your lost opportunity of doing other things with the land is going to change your timber rotation. So in other words, you're going to ask more from your timber rotation. It needs to give you more in order to compensate you for the lost opportunity of what you could be doing with the land instead. And so that's what we're sort of saying is, how does the intrinsic value of the land change the rotations? And this is really important for conservation, because you can have somebody who's had land out there that they have just been allowing to grow and grow and grow, and suddenly something happens next to them, which changes the value of that land. Someone finds oil or something like that. Now that person still owns the land, and so they can operate it as much as they want. But now that it has an alternative use for it, it is going to change how they manage the land. And so, that's kind of why we need to include this. All right, so we are going to introduce a couple of new variables here. And one of the variables, S, is going to be the site value. And the other one, D, will be the cost of replanting after a harvest. And so after a harvest, you could either, so after harvest, you either, this is after, sell or replant. So you could sell immediately, and if you sell, you get S out of it. Or if you wait and harvest next year, then you can replant at that cost D. And so if you choose to replant, you're going to have to pay the D. But if you sell, you get the S. So, if you choose to sell, then you get S. Choose to plant, then you pay D and lose S. Because it's lost opportunity. You've lost S. So that's what we're trying to model here. All right, so the way we do that is to set up another one of these no arbitrage conditions. And by the way, I'm going to assume S is greater than D in all of these things. So I'm assuming that the site is worth far more than it costs to replant it. So that's just a background assumption to make this thing go. All right, so in order for me to adjust my Wicksell logic to deal with selling, then I just need to adjust the this year and the next year formulas. And so what I'm going to say is that my option 1 is to sell. And if I want to sell, then I am going to chop down all of my forest. And so for technical reasons, I am including the cost. So if I decide to sell, then I get to harvest everything that I currently have and keep that for myself. And then I end up replanting to bring the land back to where it was. And I end up then selling it for the real estate value of the planted land, which is S. So I replanted it to bring it back up to normal, and then I sold the land ready to go for someone else to move in. And so I end up getting from them S out of that. And I then choose, and so that what I'm trying to set up here is the rotation length. So remember that I'm not solving for when to sell, I'm solving for when to rotate. But I have to keep in mind that every year that I'm replanting, I am effectively sitting on top of a site value. And so that's, I guess, another way to view, maybe that's a better way to view it, is that every year that I'm replanting, I am paying this to replant, but I also am just sitting on an asset. I'm sitting on site value. So not only am I sitting on the wood, but I'm also just sitting on the raw value of the site. And so that's my one option. So if I were to sell, I get all of this plus this right now. If I were to wait a year, then my forest is going to grow and I'm still going to have the site value, but I have to discount that. So the option 2 which will be my wait option, is that next year I will have P minus C times however much is in the forest then, minus the replanting plus the site value, divided by my discount rate, or divided by my discounting. And more and more, maybe I shouldn't have said option 1 is sell. Option 1 is cut. And I'm sorry that I said sell before. Option 1 is cut and option 2 is wait. And the no arbitrage condition is where these two things are equal to each other. And so I cut when the value of cutting, so this is, you cut when this is the case. So option 2 is the present value of cutting next year when I have more forest, but I still have the site value. Option 1 is the present value of cutting this year when I still have to pay the cost of replanting, but I also have the site value. So the site value I'm just kicking around is like principal in the bank, because I always have the option of selling and then getting a return from the bank that is not only going to be from the forest that I've cut down, but will also be from the site value here. Okay, I hope that makes sense there. So I'm sorry that I confused things when I said the option 1 was sell, but the point is I'm saying, do I cut now or cut later, given that I have this embedded site value that's in there. And so if I do a little bit of rearranging, then what I find here, and I go through the math in the notes if you'd like to see that, but I'm just going to kind of jump ahead a few steps. And that this condition is equivalent to the condition of saying that P minus C times delta V is, I want that to be, I'm going to cut when that thing falls to the level where R is multiplied by the quantity P minus C V of the current volume minus D plus S. And so I want to cut when, make sure I get this correctly, I want to cut when the rate of change falls to below this that I'm getting over here. And so I can rearrange that to say, well, that's just when delta V is less than or equal to R VT0. And then all I'm doing is dividing both sides by this P minus C. And so there's a P minus C there that gets canceled, and then it's going to be left over inside here. And I might flip the order of the S and the D. And then I make sure to keep my R in there. And so that ends up saying plus R times S minus D divided by P minus C. These are equivalent conditions. And so what I'm seeing here is that I decide to cut when the rate of growth of my forest is going to be outpaced by the rate of growth in the bank. If I were to convert all of my bank, all of my wood into dollars and put it into the bank, and then also sell my land and put it into the bank. And so this one up here is sort of in dollar. So this is kind of in dollar units. And this here is in volume. And so this version up top here is just saying the amount of dollars that I get from the growth from this year to next year is less than the dollars I would get if I just sold everything this year and then also sold the site. So it's the selling of the site and putting into the bank, which is going to affect this rotation length. And so I just rearranged it to be in our delta V form so that we can easily put that on that graph. So that this here is the so-called Faustmann rotation. And I'm hoping that you'll see that it has the Wicksell condition built into it. So this right here is just the Wicksell condition, but it has an additional offset added there to the threshold that we get from the Wicksell condition. So that's going to mean that the Faustmann rotation will be shorter than Wicksell. And keep in mind that for the Wicksell, the condition was that delta V was less than or equal to R VT0. That's the Wicksell rotation, just as a reminder. And so we've just taken the Wicksell rotation and we've added to it a little component which is representing this site value. So as long as S minus D is greater than 0, then this ends up being an additional threshold that we need to reach, and that will cause our delta V to hit it sooner as it falls. And so I can draw, let's just to see all of that together, and this will be close to where we end today, I think. We might be able to get just a little farther. So I'll go back, draw my time, T. And this here is volume per year. And so if I plot my delta V, so I'll do that, this curve, call that delta V. So you can view this as dV dt if you like, or V prime, or just delta V. So that's our year-to-year change. And then now we can plot the Wicksell condition would show up down here. So I'll draw this line that looks kind of like that. And so this here is just R times VT. So if you remember the shape of VT, you know, I guess I could have drawn it more like the shape of VT. So it's just a scaled version of VT. So it probably would have been better for me to say, draw it looking something like it rises a little bit and then comes up and then falls. But that's basically, this is just a basic shape here. It's just a scaled version of VT. And then, so that this position here, that is the Wicksell rotation. This point here, that is where we get maximum growth per, that's the maximum growth per rotation. So not over the long periods of time, but just a single rotation. And so that occurs where delta V is equal to 0. And then the Wicksell rotation occurs where delta V is equal to V of t over t. And then our Faustmann rotation, and I guess I should copy that. Maybe I'll just copy that in this condition here. Maybe. There we go. So this here is our Faustmann rotation. And we can see that the Faustmann rotation has just got the Wicksell condition plus a little bit. And so what I'm going to do is I'm going to just copy this curve that I drew for the Wicksell and shift it up to some other point, let's say right here. And maybe I'll change the color as well. And so whereas this line was RVT, this line is R times VT plus R times S minus D over P minus C. So there is just a shift upwards by this amount over here. And that shift is going to necessarily move the rotation to a shorter period. So we see that the Faustmann rotation, it's always going to be shorter than the Wicksell rotation, because all we're doing is we're taking the Wicksell line, which is just a scaled version of the volume plot, and we're scaling it up. And as we scale, and we're not scaling it up, we're shifting it up. And as we shift it up, it rides along this curve, this delta V curve, so that delta V falls to a lower threshold. And so it doesn't take delta V as long to hit that threshold. And so we get a shorter rotation, the Faustmann rotation. Okay, so if I were to go back and plot that all together in our initial plot, which is what I'll do here. Maybe I'll go here. Before that was enough time. If I go back to our original plot of just the volume, so this is time and this is volume, time, and I draw that original curve, or try to get close to it. Then this point up here, this is T max. And that occurs when delta V is equal to 0. So we wait for delta V to get all the way down to 0. Then there was the biological rotation, which I can draw in maybe with a green line. Right there. So this is our biological rotation. And and that occurs when delta V is equal to V over T. And I just realized that I think for some reason I wrote that here, and I apologize for that. That's of course the biological rotation, but that was like a Freudian slip. The Wicksell rotation is of course where delta V, if I use this color scheme, the Wicksell rotation is where delta V is equal to R VT. And that's what I was trying to show there. All right, so the biological rotation is where delta V is equal to V over T. And then in general, it will be the case that the Wicksell rotation is almost always shorter than the biological rotation, but it really depends on the interest rate. But in general, it will be the case that for forest dynamics, then we're going to have the Wicksell rotation where for the Wicksell rotation, delta V is equal to R times VT. And then finally, the Faustmann rotation will be the shortest of them, where in the Faustmann rotation, delta V is equal to R VT plus R S minus D divided by P minus C. And so that gives you a general idea that that rotations, shorter rotations, correspond to higher delta V thresholds. And the delta V threshold is somehow related to the opportunity cost. And so as there's more and more opportunity cost, then you are asking your forest for a faster growth rate. And it can only give you a faster growth rate up until a particular time. And so in the Faustmann rotation, you stop very early. Because after that point, the forest is just not worth it to you anymore because you've got so much value tied up in the site. And so that site value means that the interest you could make from the bank is so much greater. And that's the reason why you end up allowing or not allowing the forest to get into its slower region. In the Wicksell rotation, you're forgetting about the site value. And because there's no site value, then you allow the forest to grow a little bit longer because the interest you could get from the bank is not as high because you don't have this extra chunk of site value that you can also turn into the bank. And then in the biological rotation, you're not worried really at all about the economics of it. You just want to maximize wood growth. And then in the kind of this maximal thing here, this rotation here, this kind of the naive rotation, then you're allowing the forest to live out its full life, but you're not going to generate the maximum amount of timber. And so there is an opportunity cost there. It's the timber that you could be generating in this fast period. So with more opportunity cost, you get shorter and shorter rotations in general. And that's, I think, about where I want to stop today. Are there any questions?
You said for this that we should assume that S is greater than D. Will we look at like places where D is higher than S?
No, not in this class, or because that ends up being sort of a more trivial case. So the idea is that like if the amount, if it costs you more to replant than it does for you to just sell, you sell. So the idea is that if it's so costly to run a timber farm that you would just always get a better deal from selling the timber farm, then you just don't keep a timber farm. So I guess that's the reason I'm saying that we assume S minus D is greater than 0. That it helps ensure the graphs that I'm drawing like have the right shape. And in the other case where S would be less than D, it's kind of a pathological case where we wouldn't be worried about rotation length. We just wouldn't have any timber farming whatsoever.
Right, that makes sense.
An example where the Wicksell rotation is longer than the biological rotation would be if you have an extremely a low interest rate. So basically, the when the R is equal to 1 over TBR, then Wicksell and biological rotation are equal. At any lower interest rates, then the Wicksell rotation will be longer than the biological rotation. So you can view the Wicksell rotation here. If you make the interest rates smaller, then this corresponds to an interest rate of 0. If you make the interest rates larger, then this corresponds to kind of an infinite interest rate. Any other questions?
I got a question regarding the time value of money.
Yes.
I was confused. What part you changed? Where did you were you meant to say that the present value of harvesting this year is supposed to be greater than or less than the present value of harvesting next year? When you
Let me
changed
go
it.
back and let me go back and look at that to make sure I correct it. But I just realized I didn't give the attendance question out. So let me also give the attendance question, which I'll put in the chat, which will be, is the Faustmann rotation shorter or longer than the Wicksell rotation? That's the attendance question there. All right, so I'm sorry, you said when I change with the time value of money, the less than equal to or the greater than or equal to. Do you want me to go back
Yeah.
to that slide?
Yeah, you can go back to that slide because you said there was an error for a second. Like, was the present value of harvesting this year supposed to be less than or equal? Sorry, less than or greater than the present value of harvesting next year? Because you changed it.
Let's see. The time value of money here, that so I think this is the correct formula here.
Okay.
You cut when the present value is greater than or equal to, and I believe that if you rearrange all of this, that this will also be a greater than or equal to. I think that when I copied to the previous page, this is the one where I accidentally started as a greater than, but it should be a less than. So the idea is you cut when the growth of the forest drops to this point.
Okay.
Okay. Any other questions? All right. We will add habitat value in on Thursday and see how that changes things, and then start talking about fisheries, a totally different type of renewable resource where you usually don't worry about the time it takes for them to replenish as you do
Uh,
with the trees. Go
and
ahead.
another one last question before we head out. So the homework assignment that is due on the 15th, this type of stuff we went over are some of the questions involving this type of problem, the Faustman rotations, the Wickman rotation.
The
No?
homework assignment due on the 15th is all about non-renewables. So it'll all be
Oh, okay.
about stuff leading up to Hotelling's rule. The homework assignment I haven't released yet, but is on the books to release, will be about renewables.
Okay, got it. Oh yeah, this is still regarding renewables. Okay, just making sure.
Mhm.
Okay,
Yep,
thank you so much.
sure.
Thank you.
Yep.
Thank
Have a good
you.
day. Thanks.